Hi guys, long time no see because I've been like super busy and I couldn't make any videos because because my job has started. It's been around 10 days since I'm working at my job, and like it's not like those normal jobs which do not require that much effort. We've been working for a long time, so I don't get any time other than my whole day goes there. So yeah, that's that. And it's like, but actually what's sad is that today is Saturday and today I'm supposed to be free. It's a holiday and I can enjoy and have fun, but actually I'm getting bored because I guess I enjoy the work. So uh, like uh, I think weekdays are better. And I guess like I mean that's a nice thing, but I guess that's kind of sad because like I'm not able to enjoy what I'm supposed to enjoy. But anyway, so since I'm free today, I'm just gonna do this contest, Leetcode Biweekly Contest 80. And yeah, so that's what this video is about. I'll be solving these questions and I'll be explaining the solutions as I'm doing that. Yeah, so the first problem is strong password checker. And in this problem, we have to, I guess we have to check if a password is strong. So a password is said to be strong if it satisfies all of the following criteria. So it should have at least 8 characters, and it should have at least one lowercase character, at least one uppercase character, one digit, and one special character. So the special characters are characters that are given here and nothing else. So these characters are considered special. And then it should not contain two of the same characters in the adjacent positions. Okay, so if like a continuously shouldn't be there, but a is allowed. Okay, so any two characters in the adjacent position are not allowed. And given a string uh, password, return true if it is a strong password, otherwise return false. Okay, so we are given the string password in input. So the first thing we can do is we can just check the length. So if the password dot size, if it's smaller than 8, then we can just straight away return false because this is not a strong password. And yeah, after that we can perform the other checks. So I will just keep some boolean variables. Lower, this is equals to false, upper equals false, special equals false, digit equals false. Okay, and it's easy to check if all of these things are there in the password. Just go through the password character by character. Okay, and check if all of these things are there. So to check if a lowercase character is there, just just check this condition. So yeah, if the character is between small a and small z, then that means there's a lowercase character in it. So yeah, lower equals true. And same way we can do it for upper as well. For that we need to check if there's an uppercase character there. So we can say upper equals true. And then similarly we can do it for digits as well. For that we need to check if something between 0 to 9 is there in the string, then we can say digit equals true. Okay, now we have to check for the special characters. So these are a lot of characters and they are not in a continuous range, so we cannot check it directly like that. What we can do is we can instead of checking them one by one, we can just store them in a string or something. So I can just store it in a string special chars. Okay, in this special char string I'll just store this whatever these characters are given. And now what I want to do is I want to iterate on all the characters of this string. Let's say char d in the special characters. Okay, I just misspelled it. So yeah, so if c equals d, then that means there's a special character in there. So I'll just say special equals true. And yeah, so I get all of these four things, and I can just say if not lower or not upper or not digit or not special, if any of these are missing, then just return false again. Okay, Now only one check is left, and that check is it does not contain two of the same character in adjacent positions. So to do this one, what we have to do is we have to run a loop like this. For int I equals 1, I is smaller than password dot size and I plus plus. Okay, so like this, and now we have to check if this character is equal to the previous one. So if password I equals password I minus 1, so if this character is equal to the previous one, that means two adjacent characters are equal, and then we can return false. But if we reach the end of this, that means nothing, like we never return false, that means everything was fine. The length was at least 8. We had lower upper digit special, all of those, and we couldn't find any two adjacent characters that were equal. So in this case we can just return true. And let me use this example test case and run my code. Okay, it shows pending judging. True false false, which was supposed to be the output. So I'll just submit this. It shows pending, and I guess it goes green when once it's done. Okay, accepted. So yeah, first one is accepted, and it went green. So yeah, we can go to the second one. Second one is successful pairs of spells and potions. Okay, so we are given two integer arrays, spells and potions, and the lengths of them are n and m respectively, where spells represent the strength of the ith spell and the potions the strength, okay, the strength of spells and potions. So we are given an integer success, and uh, a spell and potion pair is considered successful if product of their strengths is at least success. So return an array of pairs where pairs I is the number of potions that will form a successful pair with the ith spell. Okay, number of potions that form a successful pair with the ith spell. Okay, I guess if I understand the question correctly, it's like we are given actually two arrays. So one is for spells like this, like 513. Just a second. So yeah, 513. So one array is like for the spells, and then the other one is for potions. Okay, and then we have to return for each spell, we have to return how many potions will form a successful pair with this one. So like success is 7, that means we want the product of this with some potion to be 7, and we want to count how many potions can do this. So 5 into 1 is just 5, so that won't work, but anything else will work. So that means for this one the answer should be 4. For this one the answer should be 0, because 1 times 5 is also smaller than 7, so it won't work. And then for this uh, it's like 3 times 3 is 9, 3 times 4 and 3 times 5 will work, but 3 times 2 won't work. So there should be 3. So 403 is the output which is given here. So yeah, and considering the constraints, n and m are both 10 to the power 5, that means both of them are quite large. So we cannot just, we cannot just iterate on both of these arrays. We cannot just iterate on both spells and potions, and then that, because that would be O of n times m, and that would be too slow for this problem, and that won't work. So what we want to do is we want to do something faster, and for that we want to see what is like what we want to do is we want to do it faster, like something like n log m or something like that. So what we can use is binary search here, and you might be thinking, how will we use binary search here? So we can use binary search because like for each number we just have to find the smallest, for each spell we just have to find the smallest or the least strength portion that can form a successful pair with this. Like with 3 we just have to find the smallest value out of these such that the product will be at least 7. So for this one we have this 3. So yeah, and once we find that, we can automatically we automatically know that all the larger ones will work. So if 3 times 3 works, then 3 times 4 and 3 times 5 or 3 times 100, all of them will automatically work. So yeah, I guess like that's the whole point of this. And to do this, as I said, we have to do binary search. So that would work if we have the second array sorted, which we might not have. But what we can do is we can actually sort this. So we can sort it on our own, and then we just have to solve it for each spell. So yeah, so we are given the vector of spells, potions, and the success thing, long success. So what we want to do is, first thing would be, I would just sort all the potions. So just sort potions dot begin, comma potions dot end. Okay, right. So I sorted all the potions, and then for each spell I just have to do a binary search to find the smallest potion for which there would be a successful pair, and then I would be done. So just have a vector of answer. Okay, okay, and I will just return this vector at the end, return answer. Okay, and in this vector I will populate the values. So what I want to do is I want to go through each of the spells for int x or for int s in the spells. Okay, so I have the spell s, and for this spell I have to find which of the potions will like work for this one. Okay, and whatever answer I get, I will just push it into this vector of answers. So let's just say uh, first of all, let's say int m equals the number of potions. So that is potions dot size. Okay, so we have lower and upper in binary search. So let's say the lower is 0 and the upper is m. Okay, so while, okay, and we also have the result. Let's say this is also m. I'll explain what I'm doing. So yeah, while the lower is smaller equal to upper, we have mid equals L plus U by 2. That's just how binary search works. Okay, and then what we want to do is we want to see if the mid works. So if yeah, if one LL, so one LL will just typecast into long, because if we try to multiply both integers it might overflow. So we will first typecast into long, into S, the spell, into potions mid. Okay, let's just make this m minus 1. Okay, I'll just explain what I'm actually doing. So if we multiply s with the with this mid potions, and if this is like greater equal to success, so that means this works. And if this works, so what we can do is we can say that like the result could be this, result could be our mid, but we want to find like the smallest, like we want to find the smallest index for which this works. So we would just say u equals mid minus 1. Okay, otherwise we would just say L equals mid plus 1, because mid didn't work. That means something bigger than that might work. So now the result, the RES stores the minimum index such that like if we take things to the right of it, then all of them would form a successful pair. So that's why initially I had the value m, because if we cannot form a successful pair with this spell, it would just give m, and that means none of the elements in the array are actually doing that. So now we will just say the answer at this step, or the answer dot pushback would be the number of elements to the right of this index, and that is just m minus the result. Okay, so if none of the elements could do it, then the result would be m, and this would be 0. And if all of them could do it, then the result would be 0, and that means we have m elements. So I guess this is fine. I'll just use example test cases to run this, and wait a second. So answer is 403 and 202. and 403 and 202 is the expected output. So let's see if this works. I'll just submit this. If it works, then I'll explain a little bit more about what I actually did here. Okay, yeah, so it's accepted now. Now this part is just a binary search, and this binary search. So what I did is I sorted the portions, because as I explained, we just have to find for each spell the smallest portion that would work, the index of the smallest portion that would work, and that's what I'm storing in this result. So result, I just want it to be equal to the smallest index that will work. Okay, so for that I'm doing a binary search. So this part is a binary search, and like if I have L and U, normally how binary search works, and I divide it into two parts. I take the middle part. Now if this works, then this could be the result, but then we have to find something on the left of this. That means, because we want to find the smallest thing, right? So if this works, so this works, but we have to find something even smaller than this. But if this doesn't work, so this doesn't work, and we will try to find something on the right of this. So that's why we have u equals mid minus 1 and l equals mid plus 1. Finally, when we have found the index for which it works, so since the indices are like from 0, so we can just do m minus the result to get all the values that are like that would work if from the index. So res is the index, and then m minus res is the other number of values that are greater or equal to this index. So yeah, this also works. It would be green, I guess. Yeah. And then I have this match substring after replacement. So what we are given in this problem are two strings, s and sub. Okay, and we are also given a 2D array of character mappings, where old I to new I, we're mapping old I to new I something, and I'll have to see what these are. So you may replace any number of old I characters of the string sub with new I. Each character in sub cannot be replaced more than once. Okay, so only once we can do it, but we can do it. So return true if it is possible to make sub a substring of s by replacing 0 or more characters according to mappings. Otherwise, return false. Okay, so yeah, substring is a contiguous non-empty sequence of characters within a string. So what we want to do is we have this whole thing, and we want to make this sub a substring of this. So like we want to find lead somewhere in here, but that won't work. So what we can do is we can replace the e with 3, so it will be L3ET, and then we replace the t with 7, so it becomes L3E7, and then L3E7 is present in here. So yeah, so that's how we find a substring of s there. So yeah, so that's what we want to do. And okay, here it is false, and in this one I guess we can replace d with b, yeah, and then e with 3. So yeah, so yeah, we make this L33TB, and that's how it works. So first of all, in this problem, the good thing is that the lengths of strings are not a lot. That means we can actually do like a if the length of s is n and this is m, so we can do O of nm here, and we can basically iterate on both of the strings, and that's a good thing. So what I think might be the solution is we can pick any starting position, like anywhere in this string we can pick the starting position. It could be here, it could be here. So basically like yeah, let me just, yeah, so whatever string is given, FOOL3E7BAR, whatever, and then we are also given this leet. So what we want to do is we want to try to match this lead, and after some replacements, with either this or this or this or this or this or this or this. Okay, so any of these we have to match it, and each of them we can do it each of them in the time uh, same as this length, because like that is allowed. The lengths are not a lot. These are only 5,000. So that's all we have to do, I guess. And to make this check a bit faster, what we can do is we can actually store, like we should be able to quickly process if we are able to convert a certain character into a certain other character, because otherwise this check might be too slow. You might have to go through the entire mapping, and that part would be slow. So we want to avoid that. So I'll just write the code in a way that it's easy to understand. So n equals s dot size, and then m equals sub dot size. Okay, now what we want to do is we want to pick each of the starting positions. For int I equals 0, I is smaller than, now we would pick n minus m. Okay, because we don't want to, like, we want to pick this as a starting position of a string of length m. So that's why we can only go till n minus m and I plus plus. Okay, yeah, we will start at I equals 0 and we will go till n minus m. So now from here we will make like a string from I till I plus m minus 1. Okay, so we will consider the string and we will try to make it same as the as a string sub. Okay, so basically the s, like this part of this, should be equal to sub. Okay, so that's what we want, and for that we have to check for each character whether it can be mapped to that or not. Okay, so like basically from this string we have to check if this character matches with this character or not, either with or without replacement. Yeah, so we can just iterate using j on the second string, on the substring basically. Okay, and then what we want to do is we want the jth character to match with the I plus jth character of the string s. So we want to match sub I with s I plus j. Okay, and we want to do this. So we want to do this efficiently. How will we do this efficiently? How will we check if one character can be changed into another character? So for that, I like, there might be other ways to do this, but what I am thinking is just like, I mean, there are honestly a lot of ways, and what I'm thinking is we can just keep an array. We can actually keep like a 2D array of all the characters basically. So we can keep like a table of all the characters A, B, C, D, E, and so on. And then here also we can keep a character of A, B, C, D, E, and so on, right? And then we will like if B can be changed into A, just put a tick here. If D can be changed into C, just put a tick here, and so on. So like this we will do that. And obviously we can choose to not replace it. So obviously A can be changed into A, B can be changed into A, because that just means no change, right? So yeah, so all of these are true, and something like a table like this we can make. So that's what I'm trying to do. And yeah, okay, so for that I will make like a vector of vector int or char, actually boolean, because we just have to see if like we just have to see if it's true or false, if it's allowed or not. Okay, allowed. Okay, and let's say 256 comma 256. So why did I take 256? Because the ASCII values of the characters are up till 256. Okay, so yeah, now I will just pick all of the characters, and like I can just go from 0 till 256. Okay, and I will just say allowed of I comma I is always true. Okay, because any character can be converted into itself. That just means not changing it at all. And then apart from that, using the mappings also, a lot of other things can be done, right? So I'll just iterate on the mappings for auto x in the mappings. Okay, you might not be familiar with this, so whatever. But yeah, this will just go through each of these one by one. So x0 can be changed into x1, right? So x0 can be changed into x1, old new. Okay, so that means allowed of x0 x1 is also true. So now I know exactly uh, what all changes are allowed. So what we want to do is we want to change sub I into uh, s of I plus j, right? So if it is like not allowed, so if it is not allowed to change the sub I into s I plus j, okay. So if it is not allowed, then like I'll just say boolean of okay, this works. Okay, so this is true. But if this change is like not allowed, so no, this doesn't work. Okay, right? So if this change is not allowed, then obviously this doesn't work and we will have to try another starting position. What do we have to return? We just have to return true or false. Okay, so right after this loop, if okay, this works. So if it works, then just return true because we finally found a string such that at all the positions of this substring, we can match this with the corresponding character of the original string, and it is allowed to make the change, or if we don't make a change, then also like we can finally match all of the characters. But if we reach the end of this loop, then that means that none of the starting positions actually worked for us. So that means we have to return false because we couldn't do it. So again, I'll just use the example test cases and I'll run this code. Let's see if it works. The expected output is like true, false, true, and I'm getting false, false, false. So okay, there's some error definitely, and we have to fix it now. I'll have to see what I did wrong here. Okay. Mm-hmm. Okay. This is a bit bad. I don't really see what I missed. Oh, sorry. This is sub j, right? Yeah, a small typo. We have to match sub j with the s of I plus j, obviously. So yeah, now it's true, false, true, which is what we expected. Oh, true, false, true is the expected answer. True, false, true. Yeah, so actually we had to match sub j with the s of I plus j. I just made a typo there. And now it should work. Okay. Oh wow. Okay. Nope, doesn't work. I guess I missed. I guess this condition is wrong because if n equals m, then it should still work, right? Yeah, it's plus one actually. Yes. Yeah, we are allowed one more time. Okay. Yep. Probably that's what's wrong. Okay, yeah. So there was a small bug there, and I wrote like I do a lot of off by one errors. But yeah, so when I wrote I is smaller than n minus m, the problem was like, okay, this was simple. I should have seen it. But yeah, so if the first array is like of size 4 and the second one is of size 3, so when we are at this position, the problem is that I equals 1 and n equals 4, m equals 3. So the problem is n n minus m, which is 1. I is actually equal to 1, and at this point I was like exiting the loop. So basically we have to do I should be smaller than n minus m plus 1. So it actually comes from the last index that we're accessing. So that is I plus j, and j can be up till m minus 1. So since j is smaller or equal to m minus 1, that means uh, I plus j, which is the last thing that I'm accessing. So I plus j will be at max this thing. So the maximum value of I plus j is I plus m minus 1. Okay. So I plus m minus 1 is the maximum value of the position that I would access from S, and that has to be smaller than n. So obviously I is smaller than n minus m plus 1. And that's what I missed here. That's why I was getting a wrong answer, but now it's fixed, so I got accepted. Okay, right. Now we have to count subarrays with score less than k, and the score of an array is defined as the product of its sum and its length. Okay, so we add everything in a subarray, and then sorry, we add everything in an array and multiply it with its length, and that's the score of that. So given a positive integer array and an integer k, return the number of non-empty subarrays whose score is strictly less than k. Okay, so we have to find the number of subarrays such that their score is less than k. So first of all, we have to notice that the numbers are positive. So if we have like I guess like the first observation is definitely that if we have any array such that its score is more than k, so if we add an extra element to this, that element would at least be 1 or maybe something bigger than 1. So obviously the length is also increasing and the sum is also increasing, and the score is sum. The score is just sum multiplied by the length. So if we are increasing both the length and also the sum, so obviously if we are increasing both length and sum, then definitely the score will also increase. So if we can find a subarray such that it's not good, like I'm calling it good if the score is less than k. So if the score is greater or equal to k, then it's not good. So if we find a subarray such that it's not good, so any subarray bigger than that containing the same elements would also not be good. So what I'm trying to say is, if I had this array and this sub array is not good, then definitely this also would be not good, this also would be not good, and so on. But if this is good, then obviously smaller ones will also be good. This will be good, this will be good, this will be good, and so on. And that's because when we take like a smaller sub array from here, it has less sum and less length. So if we decrease both sum and length, definitely score will also decrease. So I guess this is also like a binary search only. So we can go to each of the indices, and from here we can binary search the smallest the largest length such that all of these are good. Okay, because like if this is good, then definitely all of these are good. So we can do like a binary search here. So yeah, that's it. Okay, and we also need to have the actually we don't even need a binary search, I guess, now that I think about it, because yeah, we can do it using two pointer as well. We can do it using two pointer as well, because like let's say for the first index up till here, all of the like you can do it using binary search as well and using two pointers as well. So with binary search you'll have to use prefix sum to quickly get the sum in the range, but using two pointers you can do it more easily. So the point is like if this sub array works and this does not work, so we can just move this pointer ahead and we can say that okay, maybe this one works, right? Because like if this worked, so this definitely works, but this might not work, right? So that's why we are checking for this, and if this works we will check for this and so on. So yeah, I guess what we have to do is for each index we will try to find the last index such that all of these work, and then once this stops working we will just move this ahead and then check for this and so on. Yeah, so this in this way we can do a two pointer. Now we don't even need prefix sum, we just need a variable to store the sum. Okay, so the running sum basically, and then okay, right? So let's say int x, which is the first pointer, so this is 0, and we also need to have the length of the number. Int n equals nums dot size. Okay, and int y equals, let's say, -1. Okay, because we want to find the last index such that it works, but we don't know if 0 comma 0 will work, so I'm just going to start with -1. Okay, so we'll just go while like while x is like smaller than n or something. Okay, now what we will try to do is we will try to increase y. Okay, so if or just say while y is smaller than, or let's say y plus 1 is smaller than n. Okay, and so because we are trying to increase y, right? So while y plus 1 is smaller than n, and if we like add the y plus 1th element, so nums of y plus 1, we will add this to our sum. Okay, okay, so this will be our new sum when we include the y plus 1th index multiplied by the new length. So what will be the new length from x till new y? So this is our x, and if this is the y plus 1, so it is like y plus 1 minus x plus 1. Okay, so the length would be y plus 1 minus x plus 1. So we are adding 1 because like if you count the numbers from 1 till 3, it's actually 3 minus 1 plus 1, which is 3. So yeah, y plus 1, because this is the right index, x is the left index, and we add plus 1, r minus l plus 1. So if this which is the score, okay, so if this is strictly less than the k, okay, so that means y plus plus is allowed, because this also works, and we are trying to find the maximum y for this, for which it works. Okay, and yeah, and here we can just say if y is like smaller than x minus 1, y equals x minus 1, because at least x minus 1, y should be at least x minus 1. Okay, because if it's like very small, then there's no point. So Hello. Yeah. So I guess this will work. What I did is till here I found the max index y such that um, the subarray x till y is good. Okay. So I found that, and I know that all the smaller subarrays will also work. And I'm only considering the ones that actually start at x. So the number of such subarrays is actually y minus x plus 1. Again, you like, because it's inclusive, so you have to add 1. And since we have to calculate the total of all such subarrays, so I'm having a long answer in which I'm adding all these. And this has to be long because um, for a array of size n, the total number of subarrays can be up till nc2, and nc2 is around n square. And since this is like 10 to the power 5, so it can go 10 to the power 10 or something. So it might overflow, and we want to avoid that. So let's use sample cases and see if it works. Our expected output is actually, I guess, 6 and 5. And we got time limit exceeded. Okay, time limit exceeded. Maybe this is like an infinite loop. Okay, wait a second. What? I mean, this has to be a time, this has to be, okay, yeah, the problem is that I'm not increasing x, right? So x plus plus. Why am I missing the simplest things? And the output is also wrong. Wow. Okay. So to debug it quickly, what I'll do is for each x, I'll just print the y. I missed the time when I used to be smart. Lol. Okay. I'll just print the y for each x. Okay, so for 0 it's 1 because 2 plus 1 is like 3, and 3 times 2 is 6, and k is 10, so it works. Wait a second. For 4 it's 4 because 5 times 1, 3, it's 3, and k, wait a second. Non-empty. Yeah, okay, I guess I'm only counting non-empty ones, right? 2 plus 3, 5. What? 1 till 3 shouldn't work, right? Ah, okay, I got it. Yeah, so the problem here was, okay, I did something very dumb. So I actually have to add that to the sum. So yeah, sum plus equals nums of y. And when I do x plus plus, then obviously sum minus equals num of x. We also have to maintain the sum of the like sliding window that we have, like the space between the two pointers. We need to maintain the sum of that as well. Nums. Okay. Right, 6 and 5. Okay, that's fine. Let's just comment this or just remove this. And obviously it works, and I'll just have to submit this. So yeah, that's the lesson. Wow, okay. That was a bit too early for the lesson. 26, wow, that's a lot. Why is it 26? Hmm. What? I don't get it. I think here we also have to do sum equals 0, because like, yeah, because we are subtracting nums of x, but then if that was already not there in y, so then we would have like a negative sum or something, and that's why is the problem. So yeah, so that's the like, okay, yeah, it works. So that's the lesson here, and the lesson is that, like, if like me you stop practicing for months, you might mess up even very simple problems. Or yeah, so that's the point. Like, you need to be consistent, otherwise uh, even with very very simple problems you will make silly mistakes. You will miss lines, you will um, you know you will just make silly mistakes, and you won't be able to do as well if you're not very consistent. And so if you like, that's why you need to be regular, maybe at least 3 or 4 days a week you should be solving at least a few problems, so that you don't make such silly mistakes. And yeah, otherwise, like, you might be able to think the solution quickly, but then you will be definitely missing something, and then because of that you might get wrong answers, you might get penalties, and that might slow you down. So yeah, we're done with this contest, and I'll see you next time whenever that will be. And peace out.